Thank you, I guess, for the invitation to come and speak to you about something that's very exciting for me. So I've been doing simulation of quantum many-body systems really for a long time. And I know that kind of some of you are here for quantum algorithms and others for classical. I'll try to talk about both. So this is, I guess, work that is almost finished. I'm very excited about the results. Hopefully I can get you to be excited about those as well. Before I start, I want to mention my main collaborators, Lev Barash and Arman Babakani and Amir Kalev, all of whom are at USC with me, and funding from DARPA and NSF. So I guess a brief outline. I'm guessing at least that most of you are familiar with quantum Monte Carlo simulations, but I'll talk about those a little bit, given the nature of this workshop. I'll then introduce a new type of quantum Monte Carlo, which we developed in my group called permutation matrix representation quantum Monte Carlo. And I'll try to convince you that it's a method that has some advantages over existing methods. And specifically, what I argue that we do is that we can basically, with one algorithm, one piece of code can simulate basically any condensed matter Hamiltonian. And then, so I'll start with spin half systems, and then I'll generalize to higher spins and fermions and bosons. And if I have time, I'll talk about what we can do with this permutation matrix representation in quantum computing, and then I'll give a brief summary. So a really brief introduction to QMC simulations or quantum Monte Carlo. So of course the deal is, as you all know, I'm sure, that if we have a quantum many-body system and it's a large one, that we can't really solve it analytically. There's just too many degrees of freedom. And so we either go to approximation methods, tensor networks or whatnot, or other simpler ones even. But mostly if we want to study those systems, without approximations, we go to stochastic methods like quantum Monte Carlo, where we basically sample the configuration space rather than calculate analytically the partition function or whatnot. But of course, quantum Monte Carlo is not, you can't use it on everything. First of all, of course, we have the sign problem where we have either frustrated systems or fermionic systems. Then we have this huge problem. I'll talk about what that is maybe briefly. Sometimes we have small energy gaps, like if we have first-order first transitions, then QMC will take a very long time to equilibrate. We can have classical glassiness, like these Ising models where all the I guess low-lying energy minimum energies are very far apart, and so it's very difficult to find the ground state. But what I'd like to talk about today is another annoyance, basically, which is that for each, let's say that we want to simulate with quantum Monte Carlo a system, let's say a spin system, or spin half system, a spin one system, fermionic system, on a Kagome lattice, on a triangular lattice, on a square lattice, then for each of those models, one usually needs to come up with specially tailored updates. And basically, we need to write new code and think of when will it become ergodic, what new types of moves do we need, and so on. And so if you see papers on the archive or everywhere, you'll see one paper about this model with this method, another paper about this model with that method, and so on. And it's just more than annoying. It just takes so much time. So I guess want to mention that because we wanted to kind of resolve that problem as much as we can. So to me, and I know that there are variational QMC methods and other diffusion QMC methods, and they work on certain things. The QMC to me is basically, you have a partition function. It's trace of e to the minus beta, the inverse temperature, times the Hamiltonian. And what we want to do is we want to take this partition function and we want to be able to write it as a sum of non-negative weights. If they're negative, then we have the sign problem. There could be many, many weights. We want them to be positive, and importantly, they need to be easily computable. And if we can write the partition function as a sum over weights, and the C here, the subscript C, is for configuration. So we say that we sum over configurations where each configuration has its own weight. Then if we can do that, then we can similarly, we want to study a property of the physical system. So we have this, observable A. And you have a question?
Yes, on the previous slide, just curiosity. When you mentioned that you have a sign problem and negative weights, is that related to the sign particle method, or is that something else?
I'm not sure what the sign particle method is, but I'm sorry. Okay, sorry. Maybe it is, I don't know. So when we have an operator, what we also want to do is to write that expectation value of trace of this operator times the density, thermal density matrix e to the minus beta h, also as a sum of terms. And then QMC basically tells you, you just apply a Markov chain, jump from one configuration to the next. And if you are ergodic and you have detailed balance, that you will be collecting statistics about the operator at every configuration. You collect some value, then you average them at the end. You find your thermal average of the physical operator. And the hope, again, is that there's no sign problem. All the weights are positive. And another hope, which has nothing to do with the sign problem, is that we are hoping that the Markov process will be rapidly mixing, meaning that we'll be able to kind of cover all the important weights in, say, polynomial time. Because if it takes exponential time, then maybe you should go and sum everything analytically. So that's the hope, okay? And again, I'm fine with questions. If you have questions, that's perfectly okay with me. Just to cover, I guess, the standard quantum Monte Carlo approaches, and I know there are many more, but I will, if you humor me, I'll just cover or mention, if anything, the ones that are kind of mostly known. One of them is the Trotter method, where you take e to the minus beta h, you slice it up to a product of e to the minus a smaller number times h, and line it up as a product in the hope that each slice is close to the identity, and if it is, then you can take the components of h and you can use the BCH formula, and you can write e to the minus delta t h, delta t is small, as e to the minus delta t of different components. And of course, this is not correct. This is an approximation. But you can use that to generate a Markov chain, and this is called path integral quantum Monte Carlo. Which, again, I'm pretty sure this is like the most famous one. It has trotterization errors, which can be kind of mitigated if you take many slices and so on. I guess the experts among us will not use trotterization methods. They'll use either continuous time path integral quantum Monte Carlo that was pioneered by Prokofiev et al., and stochastic series expansion that was devised by Anders Sandvik. And these are really great methods. They don't have trotterization issues, and they are work, and they are actually the main workhorse nowadays, I guess. But again, these have their own issues. I'll not go into all those right now. But again, there is a common annoyance, and the common annoyance is that you basically need to generate a new, like these are meta methods. I mean, for every model, you'll need to generate a series of updates that may or may not work. You need to prove ergodicity and detailed balance and so on. And if you go to the literature, you'll see that there's basically one paper per model. And it takes a year to write just the code to do things optimally. So this is why I guess it's good to be able maybe to do things better, even though those methods are fantastic. And this is why we kind of came up with this permutation matrix representation, quantum Monte Carlo. Okay. So I guess just a very overview, PMR, permutation matrix representation, PMR QMC, is based on I guess a novel series expansion. I'll talk about it in a second. But the most important thing is that it's parameter free and it's Trotter error free. It's fully natural. And in that sense, it's also universal and it's really abstract. And because it's universal and abstract, then I want to convince you that you can do a lot with it.
What do you mean by parameter free?
Parameter free, what I mean by that let's say you do stochastics, or let's say you do path integral quantum Monte Carlo. You need to decide on a number of slices. This is an artifact of the algorithm, right? Which you may need to optimize over. If you do SSE, you need to decide on the size of the imaginary time. So every model that you can think of, you will see that it has parameters that you need to optimize over. SSE also have this diagonal sign problem. You need to add constants, and they affect the convergence time of the method. Okay, and you'll see that we don't have any parameters. It's fully natural. I'm not claiming, and this should be obvious, hopefully, that it's not about solving the sign problem here. It's about solving many models with a single method. Yes?
Just follow-up question on what you said. What is the sign problem for the people that are...
I'm sorry. You're right, and it's a fair question. I guess in my neck of the woods, I don't need to explain it, but of course, it's not fair because I don't know you, the audience, so absolutely. So the idea that when you sample sums, like you want to sample the partition function, and you write it as a sum of weights, then the way to do importance sampling of the configuration space, you have to have these weights positive. And the reason is that you treat them as probabilities. You basically, every time you jump from one configuration to the next, you need to calculate the probability of jumping from one to the next, and it has to do with those weights. If those weights are negative, then you can't interpret them as or unnormalized probability distribution, and then you're stuck, basically. This is a huge problem because for fermionic systems, you have that. For frustrated systems, you have that. For other systems, you don't, and then you're maybe lucky. But if those weights, if you can't write the partition function as a sum of positive terms, then you're basically screwed. And this is the sign problem.
How could these weights become negative? Because I assume that you have some control over them. So
no, if you try to, well, you know, exponentiating a large Hamiltonian is a big deal. You need to write it in a certain. You know what? I will show you. I'll give you an example because I'm going to cover our method. Great question. So I'm not claiming to solve the sign problem. I'll show how it comes about in a minute. But let me just introduce you to the method in general. So what we're looking at is somebody gives us a Hamiltonian, and we choose to represent it in some bases. I call it the computational bases, and the basis states, I call them Z, denote them as Z. And then our Hamiltonian, what we do, and I know it's technical, but I think it's worth it. The Hamiltonian, we write it as a sum of what we call monomial matrices or generalized permutation matrices. What those are if a permutation matrix, a permutation is a matrix that if it acts on a basis state, it gives us another basis state. That's a permutation. A generalized permutation is a matrix that if it acts on a basis state, it gives us another basis state, presumably, times maybe a factor. So it's a generalization of a permutation. It's kind of, if you, I like to look at it as a product of a diagonal matrix D times a genuine or bona fide permutation matrix P. And I have this cartoon here. Basically, we have this matrix, and we want to write it as a sum of permutations. Permutations are or generalized permutations. Generalized permutations are matrices that you have at most one non-zero element in each row and each column, such that there is no bifurcation. When it acts on a state, it gives us another state. And the point is that each permutation matrix, you can kind of write it as a diagonal times, or a generalized permutation matrix, you can write it as a diagonal matrix times a bona fide permutation matrix. So you shove the constants that are not one into a diagonal matrix, and then you're left with a matrix of ones and zeros. That's a permutation. And yes?
So this is highly non-canonical, right? There are many choices.
That's a great question. So the answer is that, and I have it in my next slide, is that there is a canonical way to do it, because what I want to do, and you're right that in general there are many ways to do it, but specifically what we want to kind of constrict, I guess, our choices such that one of the permutations is the identity. So we have a D0 times P0. P0 is the identity, and D0 is the kind of the classical component of the Hamiltonian. And we want to make sure that the rest of the permutations, they don't have a fixed point, meaning that if they act on a basis state, they give you another basis state, not the same one. And when you restrict yourself to these choices, then you can make a canonical choice. For example...
Like the discrete Fourier transform, right? Cyclic shift.
With discrete, I'm not sure... I think I'm not sure if a discrete Fourier transform, it's unitary, but it's not permutation, because when it acts on 1, 0, 0, 0, 0, 0, it gives you a linear combination of other states.
No, but I meant that the way you write it is, the modes of it are exactly the permutation.
Oh, yes, you can look at it this way. I think it's simpler to, let's say that you have a spin-half system. In spin-half systems, when you have Pauli X's and Pauli Y's and Pauli Z's in your Hamiltonian, then really, if the Z eigenvectors are your computational basis, then simply the permutations will be the Pauli X strings, X1, whatever it is in the Hamiltonian. If the Hamiltonian has X1 times X2, note that if this guy acts on a basis state, then it just flips two spins. It gives you another basis state. So if you want to picture spin-half Hamiltonians, then by all means, these are just Pauli X's. So you want to write your Hamiltonian as Pauli X strings times a diagonal matrix. It's that simple, okay?
Is there a reason you're excluding, I mean, because we often would take a Hamiltonian and write it as a sum of Pauli strings.
Yes.
But oftentimes Y's will show up in that context. Are you excluding Y's for
Not
any
at all.
reason?
Why am I not excluding? Because a Y is a Z times X, okay? So remember that our Hamiltonian has terms that are diagonals times permutations. So if the permutations are X, then the Z times X is the Y. I'm really not excluding anything. Okay, everything is there, and everything is simple. And in fact, the D's could be sum of many terms, the D's themselves, sum of many Pauli Z's. The P's are Pauli X strings, okay? Right.
One more question.
Yeah, may I ask?
Oh, yes.
So for some systems, the number of M can be very large, is that right? In the worst case, IP can be as large as the size of the Hilbert space.
That's true, but for physical systems, you will never see that. You will never see that. Take two local Hamiltonians, three local Hamiltonians, or any K local Hamiltonians, the number of elements that you'll see is polynomial in the system size. Yes?
That's actually close to my question. So if I start from an unknown H,
Yeah.
how do I know that it has that representation, or you have to find it? Is that some prior knowledge, or does it?
That's a great question, and the answer is that if it's a spin-half Hamiltonian, this is your answer. And what I will show very briefly, because I'm going to focus on spin-off Hamiltonians, that there is a very easy way to, first of all, we prove that you can always do that. We also prove that you can always do it efficiently. And I'll even give you the prescription for any model that you can think of almost in next slide.
I can easily see it's a basis of operators, right? Just choose D to only have one non-zero entry, and then choose your a suitable permutation. Then you get a matrix with a single non-zero entry, right?
But if I don't know H, how do I choose that frequency?
Well, I mean, if you don't know H, then what do you want to do with it? You know, why do you care? Yeah. I mean, you need to have a physical representation of it. If you don't tell me what H is, I'm at a loss. I wouldn't know what to tell you. But if you have any representation of H, I can prove that you can do it easily. Okay? And I haven't shown it here, but because I have other things that I want to show. Okay? So because one of the P's is the P0, the identity, then a Hamiltonian is basically D0 plus sum of DJ, PJ, where the PJs are off diagonal. And what we do, you take the partition, this is the expansion of the partition function. We take the partition function, its trace of e to the minus beta h. We write the trace as a sum over brackets of z and z. And we expand in a Taylor series the exponential. So we have simply beta to the n divided by n factorial, and then the Hamiltonian in this particular form raised to the power of n. And now if I want to expand everything, and that's what I'm going to do, then see what happens if I expand these parentheses and remove all of them. What I will get is a sum of all the possible products for every power n. I'll get a sum of all possible products of either d0 and dj, pj, all of them. I'll see all of them because that's what I'll get. And the question is, how is this helpful? So in order to explain how this is helpful, I want to take one of those terms. Okay, just pick, there are even factorially many, I would say, terms like that. But we can focus on one, a random one that I just chose. For example, one of these elements will be d0 times d0 times d1 p1 times d0, and so on. And I want to see what happens if you sandwich it between two computational basis states. So you see that when this d0, for example, when it acts on a basis state, I can remove it completely and pull out a constant. I call this constant E of z. It's just the matrix element of the diagonal component of the Hamiltonian. Then I forget about d0. Then I have this p2 over here. P2 is a permutation. So when it acts on a z, it gives me some z prime. So I remember that p2 times z prime times z is z prime. And then comes next d0 acting on z prime. But I can remove this d0 as well. Actually, okay, so there is this d2 that I forgot. So d2 is also diagonal. It's not the d0 diagonal, but it's another diagonal matrix. So I can pull out this d2 of z prime. Again, it's a matrix element of a diagonal matrix. And then d0 hits z prime, and then another d0 hits z prime. And so we have this constant of e squared of z prime. Again, it's a diagonal matrix element, the matrix element of d0 squared, because d0 hits it twice. It hits z prime and not z, so it's e squared of z prime. And so on and so forth. Every p will change z to some z prime, z double prime, z triple prime, and every of the d's I can push out as a constant. So eventually I can write this term over there as what I call an off-diagonal core. The matrices that I cannot push out of the bracket, these are just the p's. In this particular case, p1, p1, p2. And then I have a constant that depends on the d's that are in there. And so the p's, I will call them the off-diagonal core. And you will notice that if you want to evaluate those p's, because each p acts on a basis state, gives you another basis state, then eventually when you act with the 3 p's on the z on the right, then you get a z triple prime of sorts. But if you want z triple prime as a bracket to evaluate it, it could either be 1 if z triple prime is the original z, or it's 0. Okay? So this is why. So this is what happens when you look at one particular term. Now, one thing to notice, I guess, is that if you look at all the terms, there are actually infinitely many terms that have the same off-diagonal core, because they have different d's, but the same p's. And so
is z part of what you call a core or not?
No, z is not part of the core. I would call the core just the triplet of p's, okay? But this is, just a convention, I guess. So the p's are just the off-diagonal core. And in fact, that there is, again, an infinitely many terms that share the same core. And each of them produces another constant that you can pull out. And so I will tell you in the next slide how you can group together all those constants into something that is easily computable. And this is the only thing that is magical about this method. Yes?
What do you mean by an infinite number of terms that share the same core?
Sure.
Where do they come from?
Yes, let me show you. That's a fair question. So this is one term, okay? Let's say that I have another term that instead of d0 here, there's d0, d0.
Oh, you can have a lot of these.
Yeah, of course, because I have all the powers in the Taylor expansion. I can have 5 d0s here, 10 d0s here, and so on and so forth.
They
And
come
so
from different orders in the power series.
yes, at different orders. Yes, I definitely mean at different orders, for sure.
The ones with many d0, I mean, there's a typical number of d0s and of permutations, right? So
Typical, yes, but
you can discard it.
you're right. I'm not even going to truncate the sum. I will do more than that. I want to convince you, and I will do that in a second, I hope, that you can sum all of those without even truncation and to get a simple number out of all of those contributions. But I want to focus on I guess all the terms that I can add together. They are represented by a basis state and some product of p's. The product of p's is the core, and the constants depend on the z, because the matrix element depend on the z that you're acting on. So if you want, you can, I guess, consider this pair of a basis state and a bunch of p's that act on it as a walk, a closed walk, and it has to be closed for the weight to be non-zero. You have to go back to the original z. This is the periodicity of imaginary time in QMC, by the way. So you can imagine each core like that as a walk that starts from z, goes, HP will take it to some other z, and then another p to another z, and you have to go back. And so you have what in graph theory we call it a walk, not a path, but it kind of, the ease, all the ease, the energies that you saw in the previous slide, they are diagonal energies. So they are kind of the energies, the diagonal energies of the z's that you were visiting. And the other d's actually come from the p's. Not going to go into that, but the point is that every configuration, every pair of a basis state and a product of permutations is a closed walk on the Hamiltonian graph. So it has a really nice, I guess, interpretation, graphical interpretation of what's going on. And now I want to go back to, I guess, the question that I was asked, what do you do with all those terms? Do you have to truncate? So, and I'm not going to show it because it's just a couple pages of algebra. But if you take all the contribution, all those constants for all those powers that have the same off-diagonal core, then, and there are infinitely many of those because you need to run over all the powers, then it turns out that you can write them or neatly compress them into something that is called the divided difference of the function e to the minus beta h. I'm not going to go into divided differences. This is something that I think Newton invented. It's really an old mathematical structure that I know from experience that not many people are familiar with it. However, I will try to explain to you what that is. The most important thing is that this terrible sum, that if you try to sum it on a computer, it will take you infinity time, and if you truncate it, just an exponential time, can be reduced to what we call a divided difference. A divided difference, and I'll spend 2 minutes on that, is just, I guess, a generalization of the numerical derivative in a way. So it's we have a function. In our case, it's e to the minus beta times x, where x is the argument, and it can its input is now not just this one argument, but several arguments. And if there's only one argument, then the divided difference is simply the value of the function at that input, at that one argument. So it's just this. But if you go to two inputs, then the divided difference is kind of a numerical derivative. It's f of the first input minus f of the second input divided by their difference. So this is just the divided difference when you have two inputs. When you have three inputs, you have to take the numerical derivative of the two first derivative. So it becomes kind of a second derivative, and so on and so forth. And in general, it's kind of a numerical nth derivative, or if you have q terms, then it's the qth derivative. That's all there is to it. And the function itself is, in our case, is e to the minus beta, but divided differences in general are more general than that. But this is just to kind of convince you that I'm not replacing a very large sum with something that is very difficult to calculate. In fact, we have shown that you can calculate this very easy in something that is normally, a worst case is quadratic in the number of inputs, but normally it's linear. We'll not go into that. Yes?
I have a question. So in my classes, I have to teach the derivative of the exponential for matrix valued functions. And then these generalized different quotients show up, and then there's a Feynman-Katz formula which gives you exactly what these terms are. Is that the same?
It's
the iterated powers with the theta.
It's not the same. It's different. It's this I will just, I guess, for the sake of remaining brief, it's not exactly the same. This is a more numerically unstable method, which you can make stable, but it's not the same formula. Okay, all right. And I'm happy to talk about it afterwards. That's what I've been doing for many years. So now I want to go back. Now that we have kind of compactified all those contributions, then we have a way to write the partition function as a sum of terms. And it's important to first understand that we are summing over configurations, and the configurations are pairs of a basis state and a product of p's. I call them S with this I vector index. It's a multi-index that tells you which permutation goes at which index. So it's basically a sum over basis state and combinations of products of permutation operators. And for each such configuration, we only need to calculate a divided difference, and there are other the d's that come from the off-diagonal contributions. This d over here. It's a product of matrix elements, very easy to calculate. Oops, what is that? Sorry. And so we have for each such configuration all we need to do is to calculate one divided difference. The energies, I'm sorry. Okay. sorry, if it comes back again, I'll try to do something more drastic. And I guess, sorry.
Switch off the wireless.
Exactly, that's what I'll do. I'm sorry. Let's do that. Okay, let's hope this works. I'm terribly sorry about that. And so all you need to calculate is divide the differences. And to answer the question about the weight, it turns out that the sign of e to the minus beta, this guy, is always positive, actually depending on the order of Q. And so if the Hamiltonian is all its off-diagonal elements are negative, for example, then you can shove these minus ones into this D. This D is a product of off-diagonal matrix element. You shove a minus into each one of them. And so you have a product of negative off-diagonal matrix elements, and you can show that these terms are positive, each of them. However, in the general case, you don't know that. And because the product of diagonal elements can be positive or negative, then you can have weights that are negative, and this is exactly what the sign problem is, okay? But at least, again, I'm not claiming to solve the sign problem, obviously. I just want to show you that there is a way to write the partition function as a sum of divided differences, which are easily computable.
How flexibility grows with respect to Q?
That's a great question, and so then the weights grow up to some typical Q and then die down. Q is the typical size of the imaginary time direction. And so if you have a low temperature and a large system, Q will be large, and then it will go up and then die factorially down after that. And if you have a small system at a high temperature, then Q will be 3 or 2 or 4. It's very small. And you can actually, it's a generalized Boltzmann weight, so it looks like e to the minus beta Q divided by Q factorial, something like that. We analyzed that. It's not here, but anyway, so I showed you simply how to write a partition function as a sum of configurations, but and I haven't used any parameters. There's no parameters. I did not, no approximation, no parameter, no nothing. How can I use this to show you that you can take this decomposition of the partition function to generate a provably ergodic Markov chain, which is what I'm after. Whatever Hamiltonian you give me, I want to give you a single algorithm that will solve the problem. And the way we do it, or the way to picture it, is to remember that all the configurations are pairs of a basis state Z and the products of permutations, and they have to, I didn't stress it, but they have to, the product has to evaluate to 1, to identity, because if it doesn't evaluate to the identity, then we have the Z and the Z double prime that they vanish. The weight becomes 0 immediately. So what I need to sample is all products of P's that evaluate to, all products of permutations that evaluate to the identity, and all the basis states. And covering, or being ergodic, means I need to cover all this configuration space. Covering the basis states are very easy. You just flip spins. It's a classical, it's basically what you do classically. You flip spins or you do cluster updates, whatever. But then we need to make sure that if you give me a Hamiltonian, in a second, okay? If you give me a Hamiltonian that has random P's in it, then I need to give you or generate automatically a rule that generates with a finite set of moves any conceivable product of permutations. Yes, I had another question over there, and then, yes.
So why can you impose that the product of these permutations is the identity rather than just saying it leaves this particular state Z invariant?
Oh, it's because that's a fair question. Let me try to go back. So because the permutations, maybe here, yes. So because the permutations have no fixed points, then the z's start, roaming around. You act with a p on a z, you get a z prime, you get with a p another z prime, and so on and so forth. And the only way that you can get when you apply a product of p's on a z to get a z, the product of p's, because there are no fixed points, then this product of p's has to be the identity.
So it's this canonical decomposition that you said?
Exactly. This is why I said that we can make it, and we want to make it canonical. That's exactly right. So
that's an extra property you need to impose on your permutations.
Yes, but it's an easy property. But yeah, actually, it just makes it canonical. Thank you. You had, yes.
I had a different question. So, I mean, this doesn't make it ergodic yet, no? It's an
I haven't even
update, but the
started.
probability could be zero. I mean, forgetting the piece, right? I mean, you can propose updates which visit all configurations, but...
Of course, if I have a configuration for which the product of p's is not the identity, then its weight will be zero. Because
I'm asking the converse. You say covering the z space is easy too, but imagine you make an update. I mean, imagine the z space is cut into two pieces. So you have to flip two spins at least. You propose a single spin flip, you will never be ergodic.
Oh, sure. I'm just saying, I agree with you. And I'm just saying that normally, I guess, that you know what to do classically in order to cover the classical space. The hard part comes from covering the quantum space. So I'm kind of maybe, if you want, I'm assuming that you know what to do classically to cover the...
But you do have to think about the model to make sure the updates you propose don't have a chance zero of kind of being accepted.
Sure, or at least it's not disconnected completely. I agree with you. I agree with you there, for sure. But the hard part, I guess, is to make sure that I have a finite set of moves that can cover all the products of p's that evaluate to the identity, regardless of a Hamiltonian. I don't know what the p's are going to be, but how can I figure out a set of moves that can cover all the quantum dimension space? The product of p's is like the quantum part. It's the imaginary time portion that I need to be able to cover successfully. And so the proof itself is not complicated. I just want to give you an example because I think it's better this way. So let's say that we take as an example, a spin half system. And in spin half system, the PIs are Pauli X strings, depending on what the Hamiltonian has. It could have X1, X2, and X2, X3, or maybe it's a transverse field. It will be sum of X1 plus X2 plus X3, and so on. It's strings of Pauli X's. But I know that as a group, every PI is its own inverse, because Pauli X squared is the identity. And I know that all the Pauli X strings commute. It's a group. I'm going to use this property of a group. And what we were able to prove, in fact, that to be able to jump between one product of p's to another, all you have to do is, you start with a random configuration, and then you apply either operator swap. So if this is one of the SIQ, this is one of the product of p's, you take one of the, pairs, P1 and P2, you swap them to P2, P1. That's one of the moves. The other move is you need to insert and delete pairs of P operators, because each one of them is its inverse. And so it's important that whatever move you make, the identity of the entire sequence remains the identity. So if I swap two Pauli X strings and I started with an identity, it will remain an identity. If I insert two of the same Pauli X strings, same thing is going to happen. Or delete pairs of two Pauli X strings. And then there is really one thing that this is I guess the pinnacle in some sense, is there's the notion of fundamental cycles, which I'll talk about in a second. A fundamental cycle is a product of Pauli strings that evaluates the identity, but it doesn't have any pairs in it. So none of the p's is the inverse. None of the p's appears twice, if you will. And these fundamental cycles of the model, these are the group kind of it's what we call the fundamental cycles of a graph. Let me give you an example. It's simplest. Let's say that we had a triangular xx plus zz or in a triangular lattice. Then the p's there will be x1, x2, x2, x3, and x1, x3. You will notice that if these are the p's, then p1 times p2 times p3, x1, x2 times x2, x3 times x1 is the identity. And so we need to make sure that we find all of those cycles, or what we call fundamental cycles, that we know how to generate them. And you will notice, maybe, that if I represent every permutation as a vector of zeros and ones, 0 if the Pauli x is there, and 1 if the Pauli x, 0 if the Pauli x is not in the string, and 1 if the Pauli x is in the string, then P1, for example, it's x2, x3. I can write it as 0, 1, 1. P2 is 1, 0, 1, and P3 is 1, 1, 0. And a product of p's is actually the mod 2 addition of these vectors. And so what I need to find mathematically is basically a mod 2 addition of permutations that evaluate to the 0, 0, 0. This is the identity. So 0, 1, 1 plus 1, 0, 1 plus 1, 1, 0 is 0, 0, 0. It's the same as P1, P2, P3 equals the identity. That basically means that all I have to do, you give me a P, a set of P's in the Hamiltonian, and all I need to do is calculate the null space vectors of these P's. And null space is you can do efficiently and automatically. So we have a very simple piece of code that takes the P's in and generates the null space, which means that it generates the fundamental cycles. But if I have the fundamental cycles, then I can generate every single configuration. Except with the caveat of what you said for the classical part, which I'm not covering here because I guess I wanted to focus on the quantum part.
There's not a similar problem in the quantum part?
There is no similar problem in
So the quantum contribution cannot become 0?
That's right. Yes. You can show that you can maneuver through the entire configuration space of permutations that evaluate to the identity, and there will be no disconnect. Okay. So So with those, for example, I know I don't have much time, but there's like 10 minutes for questions. Is that right? Okay. So basically, for example, if I had a sequence P2, P1, P2, P1, P3, P1, P2, etc., if I use local swaps, I can generate I can just swap them to have P1, 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 P2, 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 P3 by swaps. I remove the pairs. For example, this is pair deletion. Then I end up with P1, P2, P3, and this is a fundamental cycle. And if I know how to insert or delete it, then I'm done. So we have a set of update moves that with verified ergodicity for all spin-half systems. I'll just say that this is just spin-half. However, you can easily generalize it, and this is what we did, to higher spins and fermions and bosons, and it's not very complicated. For example, fermions, I can use a Jordan-Wigner transformation to make it into a spin-half system. For higher spin particles, the group structure is different. It's not P1 is not its inverse. It's actually P1 to the power of the times the spin is the inverse. So every time we have mod 2, we turn it into mod 2s plus 1. It's very easy to do it. It's a null space of over a different field. That's all. And bosons, I'm not going to talk about it too much, but bosons you can treat as infinitely high spin particles, and you can, again, apply really the same thing and do everything. So I know I don't have much time, but we basically have a method that can automatically generate the required moves for every Hamiltonian. You give me a Hamiltonian, it can have fermions and bosons and spin half particles and spin 1 particles and spin 5 particles, a mixture of them, if you will. And I can find very easily what the p's or what the permutations of the Hamiltonian is. This is automatic. I will calculate the null space of those, and I can automatically generate all those updates, and I can simulate the system. Of course, if I have a sign problem, I have a sign problem. That's not what I mean, but at least I have a way to ergodically cover every conceivable system. I really wanted to show you how this ports into quantum computing. I will not do that because I don't have time, but we have variants of the same thing for quantum computers, which is nice, and maybe later during the workshop we can talk about that if you're interested. But I'll just summarize that we developed a very powerful classical simulation tool that is kind of one algorithm that can address basically all, I don't want to say all because there are, but any mixture of fermions, bosons, spin half, spin 2, spin 5, whatever Hamiltonian that you can think of, you can give it to us, and we can generate a provably ergodic method to simulate it. Again, we haven't solved the sign problem, but actually there are interesting directions there. I did not talk about measurements, but we have a paper in preparation that shows that basically using the same methods you can essentially measure any conceivable physical operator, including integrated observables and fidelity susceptibility and Rayleigh entropy, whatever you choose, we can do it. And I didn't have time to talk about that, but you can use the same off-diagonal expansion for quantum computers. You just replace e to the minus beta h with e to the ith to do unitary evolution. When we have a couple papers out there that use this permutation matrix representation to do Hamiltonian dynamics on a quantum computer, which works really well and has, again, advantages over existing methods. That's it. Thank you very much.